Yeah, hi, good evening. Yeah, one thing that Chris always asks is just roughly who's maybe here just for the first time, just to get an idea of the audience. Okay, so yeah, a lot of people have been here a few times. Yeah, there are some developers who are quite familiar with Ethereum already here, and yeah, people who are new, so it's going to be tricky to give something that everyone will be able to understand, but hopefully everyone will be able to get some bits of useful information. To start out with, just a quick slide on what is Ethereum. So Ethereum is a platform for decentralized applications and truthful applications. These applications run on a global peer-to-peer network. There are no administrators and no single point of failure. This means these applications have no downtime, and anyone can create these applications. It's permissionless innovation. The truthful part is that these applications and programs are immutable, and they always interoperate as they have been programmed. So you may have heard of the phrase smart contracts. From this perspective, it is like a contract where the APIs can't change and break whoever calls those APIs. So Ethereum can be seen as a world computer that has operations for computation and data storage. Technically, it's called the Ethereum Virtual Machine, or EVM for short. A key term is transaction, and it is a single session with this world computer. So if you're interacting with the email system, you send one email at a time, even though your email could have pictures, bunch of text, but the unit in the email system is an email. The interaction unit in Ethereum is a transaction. So this talk is about gas. And the important thing about gas is it is metering for use of the world computer. So as an analogy, electricity is usually metered by something like kilowatt hours. So in Ethereum, more computation and storage will cost more gas. Now, one of the reasons for having gas is to incentivize the people who are operating the world computer. These people, miners, they get a fee for processing transactions. And this fee is determined by the metering mechanism, which is gas. So metering is different from gas, and gas is different from ether. Now, there's a spreadsheet that shows, can take a quick look. Okay, maybe not too good to do that. Well, here's a spreadsheet which shows, the different gas values for different operations in Ethereum. It's a little small now, but some of these numbers are, for doing a multiplication, it's 5 gas. For doing an addition, it's 3 gas. So that's just, and this right bit here is the Ethereum yellow paper that has, the definitions of gas for more people who want to read the actual details. So gas can be seen as fuel. Now, every operation in the EVM requires a predefined amount of gas, and that's what you saw in the spreadsheet. Now, these are predefined protocol rules, so when a multiplication costs 5 gas, and as a user of Ethereum, you cannot change that. But yeah, I'll explain that in the next slide. So transactions must provide enough fuel, first to cover its data, and that is called intrinsic gas. It's a little technical, I can mention that more later. And basically, if a transaction does not even provide enough intrinsic gas, then a miner will not even perform any computation regarding that transaction. So transactions must provide enough fuel, and they have to provide it to cover the entire execution of the transaction, to cover all the computation it requires. The good part is that all unused gas is kept by the person initiating the transaction. Transactions that run out of gas are reverted, and this transaction is still included in a block, but the fee is still paid to the miner. This is a rough overview of how gas is fuel. Now we're going to look at these points from the perspective of fees. So in the perspective of fees, I was explaining how a multiplication costs 5 gas. User cannot change that. But one thing that a user can change is the gas price. And in Ethereum, the current default gas price is 0.02 microether per gas. And what are some of the implications? When transactions provide the fuel, the originator must have enough ether to pay for that gas. All unused gas will cost 0. And transactions that run out of gas are charged for all the gas that they have used. The formula for the fee paid to the miner is gas used multiplied by gas price. And there's going to be an example here which will hopefully make it a lot clearer to most people. So, for example, there's a program or a transaction, we want it to do 3 things. Just the first thing is store the number 31. The second thing is to add 2 numbers, and then the third thing is to store the sum. Now, assuming that the store costs 45 gas and the addition costs 10 gas, here's a scenario. So you're a user or developer, and you provide 150 gas. This is depleted in the following order. You start off at 150. Now you store the number 31. The EVM stores the number 31. So now there's only 105 gas left. It then adds the 2 numbers. So there's 95 gas left. And then it stores the sum of those numbers, and there's 50 gas left. So in total, there's 100 gas used, and there's 50 unused gas, which will cost the user 0. Assuming that the user uses the default gas price, then the fee to the miner will be gas used, which is 100 multiplied by the gas price, 0.02 microether, will equal 2 microether that is required to pay the miner. And for people who just want to see a bunch of zeros, that's how it kind of looks. So there's this difference between fuel versus fee. And it's one of the less obvious things when you're initially looking at Ethereum, say, for the first time. So there's a difference between a transaction providing enough fuel and a transaction providing enough fee. And transactions are affected by both. So if you provide low fuel, that means that your transaction is only going to be doing a little amount of computation, or it's going to run out of gas. Now let's say you provide, some sufficient amount of fuel, but if you provide a low fee, then this means that a miner might not process it immediately. So it could take time before your transaction gets written to the blockchain. Now, if you specify a whole lot amount of fuel, which was one of the questions already asked here, it doesn't cost you any more because, all of the unused gas you get back. But there's some subtlety, which, I'll explain at the end, but it can delay the transaction to get mined. Now, specifying a high fee, which is another question that someone just asked, is you can specify a higher gas price so that you are giving the miners a higher fee. And because the miner will be getting a higher fee, then they have more incentive to process your transaction faster or include it in their block. These are some rough ideas about fuel versus fee. This topic will come up a few more times in this talk, and I think afterwards, it'll probably be easier to internalize. So before running a computation, the world computer needs to know if the person who's asking to do that computation can pay for it. Before running a transaction, a miner wants to know and needs to know if it will get paid. So a transaction must offer the maximum amount of fuel it is willing to consume. This offer of fuel is called gasLimit, startGas, or gas. And one of the confusing things why this same concept is described by different words is because it depends on who wrote the documentation. GasLimit is the one that we're going to go with in this presentation. It's also what's used by the Ethereum yellow paper. The original white paper used the term startGas. And then if you're a developer, a lot of the APIs, they just call it gas. So that's another reason why things might be confusing. Unused gas is refunded. So that's all there is for that so far. Now, a transaction must, we're going to have an example after this slide here to clarify things again. Now, a transaction must offer the maximum amount of fuel it's willing to consume. So as the EVM is operating, this gas limit will start decreasing. Gas is consumed with each operation of the EVM. Now, if the user only provided this amount of gas, once it's all consumed, if it's all consumed without the transaction reaching completion, then an out-of-gas exception occurs. And what happens is that the originator of the transaction pays the miner the fee for all the gas that they have used, and then the transaction is reverted. It's basically as if nothing happened, except for payment of the ether to the miner and the transaction being included in a block. So here's an example of the out-of-gas. So we're going to use the same numbers that we did in the previous example, but this time, let's say the user only provides 90 gas. So they start at 90, the number 31 is stored, so now there's only 45 gas left. They add the two numbers, the EVM adds the two numbers, there's only 35 gas left. And then the EVM is going to try to store the sum. And now this will basically hit or even go below zero, right? So the point at which it hits zero is basically an out-of-gas exception. And what that means is there's been 90 gas that's being used, and the transaction is reverted. The 31 will not be stored as the user was hoping for. And if the user uses the default gas price, 0.02 microether times the gas used of 90 means that the miner is going to get 1.8 microether. So hopefully this shows the how out of gas occurred. Does anyone have any questions so far from this example? Continue. Yes. Yeah. So the basic idea, and yeah, this is one of the things that I do mention is, yeah, you always want to offer a higher gas limit.
But how do you know how high to go?
Yeah. So there are some limits which will continue, and yeah, feel free to ask again if it's not satisfied yet. So is there a way that miners try to find out in advance how much gas a transaction is going to use before they run the computation? That was kind of like the question. And it's for these reasons. That's why a user always provides the maximum amount of fuel it's willing to consume at the start, instead of the miner trying to charge the user along the way. Oh, looks like you've used 100 gas so far, let me charge you now. Oh, you're using more, let me charge you. That was the question. So miners get whatever the fee is, that's what the miners get. And they have to decide whether they are acceptable, whether this gas price is acceptable to them or not. maybe they might want to just ignore transactions which have this gas price and only accept ones with higher prices. And yeah, miners have their own electricity costs, which are all different, so it's all up to them. Yeah, we can look at the spreadsheet or later, but there's always some cost, and then per byte there's some extra gas cost.
Is it byte time, or is this not permanent storage?
So, sorry, storage?
Is this storage like just for the lifetime of the transaction, or are we talking about storage that is?
Just lifetime of the transaction. So once you've paid it, that's it. Your data's on the blockchain. Yeah. The data is permanent, but you don't keep paying that as long as your data is in the blockchain. Once you've paid it once, it's kind of there. Going to talk about gas refund. The slide here. Okay, looks good. So there are two operations in the EVM, in this world computer, that has negative gas. And that's one is clearing a contract. In Solidity, it's using the self-destruct keyword. Sorry, someone has a question there? All right, no picture, okay. And then the other operation that has negative gas is clearing some storage in the EVM, and that has minus 15,000. Now, okay, gas refund is, it's one of the more technical things, but I'm going to try to cover the whole complete technical parts about it in this slide here. So the way the refund works is it's a separate refund counter. And the gas refund is only provided at the very end of a transaction. And then the maximum refund equals half the gas used. Okay, so the key point is that transaction offers fuel, let's say this amount of fuel, and once it offers this fuel never increases. Okay? It always decreases, and if it ever hits 0 or below, that's an out of gas exception. So the fuel always decreases, but when you run these, when the EVM runs these other, negative gas instructions, what that does is there's a separate counter. There's a separate refund counter, let's say here, which increases. Okay? Now, at the end, you have, let's say you have this amount of refund, but on this side, you have, if you've only used this amount of gas used, then your refund is going to be limited to half of it. Okay? It doesn't matter how big your refund counter is built up, you're only going to get half. And obviously, if your refund counter is just small, then you'll even just get a smaller bit. So this is a little bit technical, but hopefully that might have cleared things up for some people. Any questions so far? Okay. Now, there have been some questions already about why not always just offer a whole amount of gas so that you will never get an out of gas exception. Okay, why not always offer a high gas limit? So one of the reasons why is that there is a limit between the gas limit, the amount of fuel you've offered, and the actual gas that the transaction uses. So you could offer this amount of fuel, but in the end, you only use a small amount of fuel. Okay? Miners only get paid for the actual gas that's used. So if the gas used is only this much, even though it offers this big amount, miners only get paid for this small amount. So if you're a miner, it's going to be safer for you to mine a lot of these small, transactions, let's say 100 transactions with a gas limit of 40,000 each, than one really big transaction with a gas limit of 4 million. Because if this was 4 million and gas use was only 1 million, then the miner has potentially lost this 3 million gas of revenue. So big transactions in this sense of a high gas limit are not the top priority miners. Something like gas price would be more of a high priority for them. Now, there's another subtlety with what I said, because there's intrinsic gas. So if you do offer like 4 million gas and let's say 3.5 million of that is intrinsic gas, then a miner would like that because it's really only the difference between the intrinsic gas and the gas limit that this general slide explains. Okay, so intrinsic, I just thought of this recently after I typed this slide up, that if you have a high intrinsic gas transaction, then you have to have a high gas limit, and miners will be okay with that. So now, if you remember that the gas limit is the user specified maximum amount of fuel a transaction will consume. So how many transactions can fit in a block? And that is until the sum of these gas limits reaches the block gas limit. The winning miner can adjust this block gas limit by 0.0976%. That number is 1 divided by 1024. So every block, the winning miner can bump up this block gas limit or bring it down every block. But so this protocol rule where the miner can move it up and down, that's to help prevent stalemate, like in Bitcoin's case of the block size. That's to help prevent this kind of stalemate. But there is a minimum that if the block gas limit is here, the miners can't just keep forcing it down. The minimum block gas limit is 4.7 million, and that exact number comes from the digits of 1.5 pi. So some practical, yeah.
In terms of way, right? I guess. Sorry, gas.
Yeah, gas.
Right.
Okay. So some. Here's a point about exchanges and why sometimes when they send Ether, or if you're trying to use an exchange and you're sending Ether, why it might not work. Basically, it boils down to probably out of gas. Okay, because in Ethereum, there's two types of accounts, basically user accounts and contract accounts. Sending Ether to a user account always has a fee of 21,000 gas. Again, there's no harm in offering more. But sending Ether to a contract is a higher fee, and that fee depends on the contract code. And it also depends if data is being sent, such as, so there's the DAO contract, and usually when you're interacting with the DAO contract, you're not just sending it Ether, you're calling some function in it. And that means that your transaction is going to have data, and so basically that's just more fee. So some exchanges, maybe they're only providing 21,000 gas whenever they have a transaction, and that would be insufficient gas in some of these cases, and that's why you might have problems if you're using an exchange and trying to send Ether to some contract wallet or something like the DAO. Here's a note, just three more slides or so. Here's a quick note for developers who are debugging missing transactions. This is kind of ties into, especially in development, it's always, I think, a pretty reasonable rule that when you're in doubt, just increase the gas. Sometimes you're trying to see why isn't something happening, and it's usually because out of gas, so just increase the gas. You can check, is the from account unlocked? Check the eth.pending transactions. And then the clients themselves, they'll help guide you by giving you an error straight away in these cases, like if the intrinsic gas is too low, account doesn't have enough Ether, and block gas limit exceeded. If anyone has questions about that after the conclusion, I can mention those. So next slide is going to be the conclusion. This one here, again, is just about the difference between metering and the fee. I showed these slides, and this is one of the feedback I got to really emphasize this point. So in Bitcoin, the metering is done by bytes, basically the size of a transaction. So in Bitcoin, if you have a transaction that is this amount of bytes versus this amount of bytes, that's basically how your fee is based. But in Ethereum, you can't just meter just by the size of the bytes. You also need to meter computation, because a small amount of bytes or a small amount of code could still be written in a way that will be an infinite loop. Now, metering and fee are separate, so you could keep the gas metering and have no fees. So for example, on a private chain, you could have different rules, such as each account could have 20 million gas per day, or each account could have 5 million gas per transaction. Okay, so those are maybe just two ways that you could have Ethereum's gas metering and have no fees. Or you could also have fees, but based on different metering. If you just want to keep things simple, you could just have metering based on bytes. Now, these alternatives are just more applicable to private chains, because as we've said, if you're only metering by bytes, someone could write really bad program that just never stops. Or on a private chain, you can kind of control who your accounts are, but on a public chain, Sybil attacks, anyone will be able to just keep creating a new account to get more gas if that's what they needed. Okay, so in conclusion, the gas is metering and fuel for use of the world computer. Gas is different from the Ether fee for using this computer. And then there's a difference between providing enough fuel and providing enough fee. Out of gas costs money, and you get nothing in return. All the gas is consumed and charged, and your transactions reverted. It is safer to offer more gas, since all unused gas is refunded. And when you're debugging a missing transaction, when in doubt, maybe start offering more gas. Here are some references. It's the white paper, yellow paper, and I'll show you this, the Ethereum Stack Exchange, where it's another really good resource for it. These are the top voted questions so far about gas. So there's questions such as, can contracts pay the gas? What is gas overall? So these are some of the references. Okay, thanks. Thank you.